Machine learning has five main types, and each one learns in a different way. Supervised learning learns from labeled example to make predictions. Unsupervised learning finds hidden patterns in unlabeled data. Reinforcement learning learns by trial and error, earning reward for good decisions. Semi-supervised learning uses a small amount of labeled data along with large amount of unlabeled data. And self-supervised learning creates its own labels from the data to learn useful patterns. Together, these five approaches solve different kinds of real-world problems. Let's understand supervised learning. Supervised learning has two main phases, training and prediction. In the training phase, we give the model many examples along with the correct answers. Here, the fruits are the inputs and their names are the labels. The algorithm studies these examples and learns the relationship between the fruit and its name. This creates a trained model. In the prediction phase, we give the trained model a new fruit that it has never seen before. Using what it learned during training, the model predicts the correct label. In this example, it correctly identifies the fruit is an apple. Supervised learning is used in many real-world applications. It helps detect spam emails by separating unwanted messages from genuine ones. It can understand customer opinions through sentiment analysis, such as identifying whether a review is positive or negative. It is widely used for image classification, like recognizing that an image contains a dog. Banks use it to predict credit risk before approving loans. In healthcare, it helps doctors detect diseases such as pneumonia from X-ray images. And in real estate, it predicts house prices based on features like location, size, and previous sales. An algorithm is simply a step-by-step set of instructions used to solve a problem. In machine learning, an algorithm learns patterns from data and uses those patterns to make predictions or decisions. Different algorithms use different methods to learn, which is why we choose different algorithms for different problems. Linear regression predicts continuous values such as house prices. Logistic regression classifies data into categories like spam or not spam. Decision trees makes decision by following a series of simple rules. Random forest combines many decision trees to improve accuracy. Naive Bayes uses probabilities to make predictions and is widely used for spam detection. Support vector machine or SVM finds the best boundary that separates different classes, and K nearest neighbors or KNN predicts the class of new data point by looking at its nearest neighbors. The best algorithm depends on the type of data and the problem you are trying to solve. We will learn each one of these algorithms in detail in upcoming episodes. Unlike supervised learning, unsupervised learning works with unlabeled data. That means the data has no correct answers or categories. The algorithm looks at the data on its own and searches for hidden patterns or similarities. It then groups similar items together into clusters. In this example, the algorithm automatically separates the circles, squares, triangles, and hexagons into different groups. This makes unsupervised learning useful for discovering patterns and organizing data without human labeling. Unsupervised learning is used in many real-world applications. Businesses use it for customer segmentation, where customers are grouped based on similar buying behavior. In market basket analysis, it discovers products that are frequently purchased together. It is also used for dimensionality reduction, which simplifies large datasets while keeping the most important information. In anomaly detection, it helps identify unusual patterns such as fraudulent transactions or network attacks. It can group similar documents together through document clustering, making information easier to organize. And in image clustering, it automatically groups similar images without needing any labels. There are different algorithms used in unsupervised learning, and each one has a specific purpose. K-means clustering groups similar data into fixed number of clusters. Hierarchical clustering builds clusters step by step, creating a tree-like structure. Principal Component Analysis or PCA reduces the number of features while keeping the most important information. This makes large datasets easier to analyze and visualize. Gaussian Mixture Model or GMM groups data based on probabilities, making it useful when clusters overlap. Reinforcement learning is inspired by how humans learn through experience. An agent interacts with an environment to achieve a goal. First, the agent observes the current state of the environment. It then takes an action based on that state. The environment responds by giving a reward if the action is good, or a lower reward or penalty if it is not. Using this feedback, the agent learns which action lead to better outcomes. By repeating this process again and again, the agent gradually improves its strategy and learns to maximize the total reward. Reinforcement learning is used in many real-world applications where decisions improve through experience. It helps robots navigate and perform tasks by learning from their environment. In game playing, it enables AI to master games by learning the best strategies through trial and error. In finance, it helps optimize trading and investment decisions. Autonomous vehicles use reinforcement learning to make safe driving decisions in changing road conditions. It is also used in cloud computing to manage resources efficiently. Recommendation systems learn user preferences to suggest more relevant content or products. In supply chain optimization, it improves delivery routes and logistics. And in healthcare, it helps optimize treatment plans and improve patient care. There are several algorithms used in reinforcement learning, and each one learns in a slightly different way. Q-learning learns the best action for each situation by storing rewards in a queue table. SARSA is similar to Q-learning, but it learns from the action the agent actually takes. Deep Q network or DQN combines Q-learning with deep neural networks to solve more complex problems such as playing games. Policy gradient learns the best strategy directly instead of storing action values. Actor critic uses two models. The actor chooses an action while the critic evaluates how good that action is. And proximal policy optimization or PPO is a stable and efficient algorithm that is used in robotics, game AI, and many real world applications. Each of these algorithms has its own strength, and the right choice depends on the problem you want to solve. Semi-supervised learning combines the strengths of both supervised and unsupervised learning. It starts with a small amount of labeled data and a large amount of unlabeled data. The model learns from both datasets at the same time. The labeled data provides the correct examples, while the unlabeled data helps the model discover additional patterns. As a result, the model makes more accurate predictions even though only a small amount of labeled data is available. The more useful unlabeled data the model learns from, the better its performance becomes. This approach is especially useful when labeling data is expensive or time consuming. Semi-supervised learning is useful when only a small amount of labeled data is available, but there is plenty of unlabeled data. It is widely used in image classification, where only a few images need labels while the rest helps improve accuracy. In text classification, it can identify topics, sentiment, or spam using only a small set of labeled documents. For speech recognition, it learns from large amount of unlabeled audio to improve transcription. In medical image analysis, it helps detect diseases such as pneumonia using only a limited number of labeled scans. It is also used in fraud detection to identify suspicious transactions. Recommendation system use it to provide better suggestions by learning from user behavior. In bioinformatics, it helps predict gene function and analyze biological data. And in natural language processing, it improves tasks such as text classification, named entity recognition, and language understanding. Self-supervised learning learns from unlabeled data without needing human-created labels. First, the model creates its own learning task called a pretext task. For example, it might predict a missing part of an image or the correct rotation of an image. By solving these tasks, the model learns useful patterns and features from the data. These learned features are then used for real-world tasks such as image classification, object detection, text classification, and speech recognition. Because the model learns from large amount of unlabeled data, it performs better even when only a small amount of labeled data is available. This makes self-supervised learning a powerful approach for building accurate AI models while reducing the need for manual labeling. Let's understand self-supervised learning with a simple example. We start with an unlabeled image. Nobody tells the computer what the image is. Next, we hide a few parts of the image. This becomes the model's learning task. The model looks at the visible parts and tries to predict the missing pieces. Every time it does this, it learns more about shapes, colors, and patterns. After practicing on thousands of images, the model becomes very good at understanding images. This knowledge then can be used for tasks like image classification, object detection, and image segmentation. Self-supervised learning is transforming many AI applications because it can learn from large amount of unlabeled data. In computer vision, it improves tasks like image classification, object detection, and image segmentation. In natural language processing, it helps model better understand text for translation, question answering, and sentiment analysis. In speech processing, it improves speech recognition, speaker identification, and voice translation. Recommendation systems use it to understand user preferences and provide more personalized suggestions. In anomaly detection, it learns normal patterns and helps identify unusual events such as fraud or cyber attacks. In healthcare, it helps analyze medical images and support disease detection and diagnosis. It is also used in robotics to help robots understand their surrounding and make better decisions. For time series analysis, it improves forecasting and predictive maintenance. And in audio and music, it helps recognize sounds, classify music, and retrieve similar audio. Thanks for watching. Like, share, subscribe.